Alright, everybody. So, in today's lecture, or I mean 5 minute video, we're going to be examining what the RS type of like configuration is. So, RS is basically nothing. All it just says is that sinister and R is rectus. Now, R and S type, these are the rules of now. So these are the rules of what you would call optical isomerism. Now, as we have heard, is that for example, when there is a compound, let this be OH. So now this group, this if you were to identify the chiral carbons here, the first chiral carbon would be here, which means that this compound is optically active. All right. Now, in order to represent optically active compounds, we either take the help of the Fischer projection. Fischer projection. Now, Fischer projection is just a simple way of representing this. In what way are the bulky compounds situated at? So, for example, if I were to write this, let me just give you a question: is I H F and Cl. Now we'll keep this for later. Now, if I were to, let's say, R. Now this is how I remember is that R is like this. Okay, so R goes like this, meaning like this. So that just means that my priority, I'll just correct myself as well here. Yes. So R moves this way. So S will move the opposite way. Literally just this. And that's how I name. I mean, these are also the initials of my name. So that's how another way that I can remember them. And if I were to just hold on, erase this shit. Now, Fischer projection, for example, whenever we draw a compound, optical isomerism basically just says that a compound might be out of the plane or in the plane, and we really can't tell that because it's, well, optically means that we can only see it in a laboratory. Now, for example, if I have a compound, any compound, we all know that carbon forms sp3, sp3 hybridize like at its max, and it does a tetrahedral geometry. Now, if I were to just say C, so what we do, we generally just write this as C, let's say H, and then another bond going out of the plane. Wedge dash, this is what you call a wedge dash structure. So we generally write a compound like this. Now, optical isomerism basically talks about in if the bulky groups are on the same side or different sides. It's nothing of much matter actually. It's a very low weightage topic. And let me just go down. Now let's start talking by. Okay. So if we were to return to the Fischer projection, I so there's iodine, hydrogen, fluorine, and chlorine. Let's start off by numbering these compounds using the CIP conjecture, which basically says that the like heaviest has the lowest number. Now, in this, we can assign hydrogen a 1, fluorine a 2, iodine a 3, chlorine a 3, and iodine 4. Now, when calculating like stuff like this, we must always ensure that the fourth priority is on the vertical. I think I did it. Wait, hold on. I'm an idiot. I just did the numbering wrong. Huh. Now, if you were to look at this compound, try to go 1, 2, 3 means it like goes like this. So this compound will go like this, and as such, this will have a. I think. Wait, hold on. This goes like this, na? Yes, this will have an R type of optical configuration. Now, another rule for CIP conjecture is that if you were to have, let's say, this something where H is here, let's take fluorine and bromine again. So we'll just give this one, two, three, four. Now, according to the rule, is that this H atom should always be on the vertical, meaning that the fourth priority should always lie on this vertical line. Now, in order to do that, we just make even number of interchanges. So if I were to just place this H here, I would also have to replace this chlorine with this here. In that way, we do not change the actual configuration of the compound. Now, this was done experimentally, so even I don't know why they did that. So I just take this HBr, fluorine chlorine up. Now, what this will do is that, for example, 1, 2, 3, 4. Now, the compound now goes like this, which is still S type, which is now S type. And there's nothing really to it. If I were to tell you, uh, let's start by converting this into something. Now, for example, if I have, let's say, this structure, Fisher structure, and I wish to convert it. I wish, like, hold on, I'm speaking all gibberish. Oh, congratulations. So this is a compound. I mean, not a compound, just a skeleton. Now, if we were to convert this into this stick, what do we call this? Fisher projection. What we would do is that we consider this little thing that's in the plane that is planar as the whole, Now, I don't think I have anything to explain this. Now, do I have a pen? So just imagine that this is the planar part. This is the planar part. This goes out of the plane, and I have one finger that goes into the plane. Okay. Now what I will do is that I will the thing going out of the plane, it will move like this. Do you understand? So the thing going out of the plane now becomes planar, and the thing going in the plane, it sort of curves like this. If I were to just draw this, let's just say H F C L I. Now, if I were just to rotate this, what would happen is I would get something like this, right? Uh, hmm, like this. I don't know if you can see it. I don't have that much flexibility. Uh, yes. So this just rotates like this. So what happens here is that this Cl and this iodine and this hydrogen. Okay, here you go. We did this. Let's start by numbering this again. Now, if your hole is on the one this side, three and four and three. Now, what in this thing, we did this four, three and four. Hold on, मैं सही बताया था ना. Ah, yep. So you basically rotate it like this. Now, what happens is that this ये ऊपर जाएगा. This is four. एंड ये भाई तुम्हारे जैसे तो ये मैंने इसको ऐसे फॉर एग्जांपल जैसे इमेजिन दिस कि मैंने इस एटम को ऐसे हाँ भेज दिया इसकी तरह जस्ट स्लाइटली बेंट इट एंड इसकी जगह हाँ ले आया. तो व्हाट विल हैपन इज कि ये एक तरीके से स्ट्रेट लाइन ही बना देगा. तो फोर एंड थ्री तो फ्लोरीन यहाँ गया तो ये एफ एच सी एल और आई नंबरिंग कर देते हैं वापस से टू थ्री फोर एंड हेंस तुम्हारा क्या हो गया आयोडोब्रोमो. ठीक है. I'll just read this out if you can note this. Just do it. Fix your eyes between the planar valencies and call it the hole. Shift the valency lying on the wedge to the whole side and the other valency lying on the dash on the other horizontal side. And there's nothing really to it. Optical isomers is a topic that doesn't have a much questions. It's not very important to per se. Hydrocarbons has much higher weightage, and I would say that you practice hydrocarbons. Isomerism in general is also pretty much good. I mean, it's a scoring topic. If I were to just say that write the monochloro. Oh, wait, huh? Write the dichloro. Yeah, trichloro. Trichloro derivatives of benzene. So this is benzene. Now this is a very common mistake that I did uh, in my paper. That is, if I were to instead just draw this, all whenever you draw isomers, draw the resonating structure because that will help you understand so you don't make any errors in the valency. Trichloro. Now chlorine can be attached like this or this. Again, this, this, or this, and this, this. One, two, three, and there's another one, or not. Another quick way of knowing if the compound you've drawn is correct is to well simply check the IUPAC number of everything. Like for example, this is 1, 2, 3. This is 1, 3, 4. This is 1, 2, 3, 4, 5. 1, 3, 5. And then this is, yeah, this is also 135. You can't just say 1 2 3 4 5 6 136. Yeah, no, never mind. 136. Just don't do this silly mistake that I did. Was to attach two chlorines on one side. This is quite stupid. Don't ever do this. But you, not me. You might be better at chemistry. All right.